campus of Stanford University.
People are worried about data. They're worried about their privacy and their security. They should be. We need secure systems.
This is the future of everything.
But we can't have a system that closes that data off. It is too rich of a source of inspiration, innovation, and discovery for new things in medicine.
With your host, Russ Altman.
Today on The Future of Everything, the future of combustion. When we think of combustion, we think of burning and fires. Maybe we think of car engines, at least the old kind of cars before we had electric cars. I checked the internet and I found two major definitions for combustion. One said the process of burning something, okay. The other one said rapid chemical combination of a substance with oxygen involving the production of heat and light. Okay, good. This, I think, roughly corresponds with our understanding of combustion. But we don't necessarily think of combustion as a tool for creating innovative materials that can solve engineering problems. Can combustion be used in some way to purify water? Or can we use combustion to create new materials that are useful for making consumer products, or even harnessing solar energy and turning it into useful energy to power our electronics? Well, Professor Xiaolin Zheng is a professor of mechanical engineering and material sciences and engineering at Stanford University and an expert on how combustion, nanomaterials, and energy conversion can all work together. Xiaolin, you have created ways to use solar energy for purifying water. How does that work, and where did you even come up with that idea?
Okay, so I've been working on combustion flame-made metal oxide for a long time.
You said flame-made metal oxides.
Yes.
So this is a way to make materials.
Yes. So we use the simple way is if you think about the rust on your cooking pot.
Yes.
And that's iron oxide. You are heating it up, and you get iron oxide.
And this is the red stuff that we see.
Yes.
Literally rust.
Yes. So we're using the high temperature and oxidizing environment to make metal oxides. And that's the base material for this water purification. And,
So that sounds like it would make the water less pure. So I need to hear more about how these rust particles might help make the water better.
I see. The chemical composition is similar to the rust, not exactly the same, but the format is different. So we like metal oxide because the way we make hydrogen peroxide for the water disinfection is to oxidize water using electricity. So the electricity will provide holes, and that will oxidize the water to hydrogen peroxide. And to do that, we need a catalyst. So at this kind of whole environment, metal oxide is more stable.
Okay.
Yeah, so the metal oxide takes the holes.
So let's go back and unpack that, because you said a lot of interesting things. So first of all, water. I think we all know what water is, so we're good there. Tell me a little bit about hydrogen peroxide and what it is and what is its role in water and in water purification.
Yes, so the typical example for your hydrogen peroxide, we say H2O2 or hydrogen peroxide, is the 3%.
So water is H2O and hydrogen peroxide is H2O2. So there's an extra oxygen.
Yes.
Okay.
It's a strong oxidizer. You have 3% in your medical cabinet for most people. So if you have a minor cut and you put that there as a disinfectant to kill the germs.
Okay, so it acts as a disinfectant. At least that's one thing it does.
Yes, and hydrogen peroxide is also used for paper and fabric bleaching.
Okay.
And in your laundry detergent, some laundry detergent, especially the one has a little pop, you have a little package and put in the laundry machine, and that also contains hydrogen peroxide.
Okay.
Yes.
Okay, and so does it kill bacteria?
Yes.
And does it do anything else useful?
It removes inorganic impurities like metal ions in the water. It also removes organic compounds, like if you have pharmaceutical residues, if you have pesticide residues, all those organic contaminants in the water.
Okay, so now this is 3 extremely useful functions. Just to review, it's killing bacteria, it's helping to remove heavy metals, which can be very toxic, or even organic matter from medications or from pesticides or these things. Okay, so now you got me on board that H2O2 would be good. Now, I want to make sure that people don't start drinking this stuff because it also can be very toxic.
Yes.
And for instance, we do not drink the hydrogen peroxide that is in our cabinet. It is much too concentrated. But what I'm understanding is that a small amount of this in the water system can actually be a purifier. Is that true?
Yes.
Okay.
So take a pool, residential pool, for example, and you can use about 30 to 50 ppm, parts per million, hydrogen peroxide for cleaning up the pool water.
So this might be what the pool guy does.
Yes. So it's very, very small amount.
Okay. So now I'm a big fan of hydrogen peroxide. You've sold me on that. You're able to use solar energy somehow to create it out of water. So obviously in any body of water, there's plenty of water, but there might not be plenty of hydrogen peroxide.
Yes.
So tell us how that works.
Okay, so the system we build is called photoelectrochemical system. It's a
Photoelectrochemical system.
Yes, that means it involves 3 processes. So photo means that material absorbs sunlight, like a solar cell.
Okay.
And the electrical means once the sunlight is absorbed, they will generate carriers like electrons and holes. That's the electrical part.
Okay.
And the chemical part is the reaction between the electron and the hole with the water. So if the hole oxidizes the water, and that produces the hydrogen peroxide. Yeah, so...
And this can be controlled, so you can get as much as you need, or is it an uncontrollable reaction?
It has some controllability. I mean, the efficiency of how much hydrogen peroxide is controlled by the efficiencies of all these 3 processes.
Okay.
So you could tune the efficiency of any individual one to control the concentration.
So just to be very clear, people should be quite excited about this, if I'm understanding, because we have a lot of bodies of water, both industrial as well as just from weather, where there is a lot of impurities in the water and it's not potable, and people don't have the drinking water they need. So I think, tell me if I'm wrong, one potential future, maybe we're not there yet, is that this becomes a mechanism for routinely and relatively inexpensively purifying water. Is that part of your vision?
Yes, my vision is this will be a portable, distributed water disinfection system. Because for most of us residential water, we already have centralized the system, and that works really well. I don't think we are going to contribute in that space. But for a lot of people, for American, there may be 15 million of homes, they rely on their private water resources.
From a well or...
Exactly. And the EPA doesn't regulate what kind of water quality they have.
So the EPA is the Environmental Protection Agency of the U.S. government.
Yes. So the individual people have to rely on their own water purification system, their periodic tests to maintain their water quality. And that can cause problem. I know people who rely on well waters, and their families may have several members of people can get cancer due to maybe some pesticide.
Right, and this is one of the types of molecules that the hydrogen peroxide might be useful for.
Yes.
This is the future of everything. I'm Russ Altman. I'm speaking with Xiaolin Zheng about her work in water purification using these metal rusty compounds that are related to rust. So how did you think of this work? So, you have a background in combustion and fire and flaming and energy. When did you say, oh my goodness, I could use this to purify water, which I'm guessing was not your initial professional focus. So tell us that story.
Okay, so it's a long story.
Good.
But to keep it short, so I learned about combustion, chemical kinetics, and the flow for my PhD. And then I was really interested in nanotechnology. And I want to learn why the size will affect the properties of materials. So I learned about nanomaterials. I used silicon nanomaterials for solar cells.
So tell us a little bit about nanomaterials. Give us a little definition for how big they are and what would, if I look at something, how do I determine if it's a nanomaterial?
Okay, so according to National Science Foundation definition, nanomaterial means they have one dimension is smaller than 100 nanometers.
Okay, and that's 10 to, there's something like 100 million nanometers in a meter. Something like that. That might be off by a 0 or 2.
So if you think about if the human hair, say, is 100 microns.
Yes.
And then 100 nanometer is about 1,000 times smaller.
Okay.
Yes.
Very good. So these are very small particles.
Yes. And they're interesting because their properties become size dependent. So that means normally we think about material properties. You tune the chemical composition based on periodic table to change the properties.
Yes.
Now we can change their shapes and the size to change almost all properties. I think that's the really exciting part.
So you became an expert at this. And then there must have been an aha moment for water. How did that go?
Yeah, so I started to dream about using combustion like a flame to make those tiny materials.
Okay.
And I started to make metal oxide. And initially, I was using those metal oxide to do the water oxidation, very similar process to oxygen. That's the typical one known as water electrolysis.
Right. So you go from H2O to O2.
Yes.
And O2 is oxygen. That's what we breathe. That's what we love
Yes.
oxygen.
Yes.
More or less.
Yes.
For life.
Yes. But most metal oxide, I mentioned there are three processes. The metal oxide has very poor chemistry for the whole to oxidize the water, right? So if they're not oxidizing the water to oxygen, they must be doing some other reactions because the whole has to do something.
Right.
Yeah, so the hydrogen peroxide used to be a side reaction.
So this was, in some sense, the H2O2 was a failure because you weren't getting the O2 that you wanted.
In a way, yes, yes. And then once we think about, okay, now we get hydrogen peroxide, what's the use of hydrogen peroxide?
Bingo. And then then there's all of these uses that you described.
Yes.
So did you eventually succeed in getting the O2, or did this totally redirect your research to H2O2 and now we forget about oxygen?
I think for research, we are interested in the fundamental selectivity, say, how can we tune to O2 versus hydrogen peroxide by choosing different materials?
Now, you said something in that interesting story, you said something in particular that I want to ask you about. You said, can I create the nanomaterials using combustion? So can you explain? So do you actually take some starting material and kind of burn it and it turns into these little tiny particles? And how good are we at making sure we get exactly what we want and not a lot of other contaminants?
I see. So the way we call it flame vapor deposition.
Flame
Vapor deposition.
Deposition, okay.
I borrowed the name from chemical vapor deposition.
Okay.
So the idea actually is very simple. If I take, say, tungsten oxide, tungsten is the electrical thing for the lamp.
Okay, yes.
Yes. So it's a common metal. So we want to make tungsten oxide nanomaterials. What we do is we use tungsten metal as a precursor. So and then we put the tungsten metal near to a flame, a post flame. Say if you think about you have the burner on your cooking stove, you just put the tungsten above it.
Okay.
And then the flame is very hot. And the flame also have some oxygen left over. And
So it doesn't completely burn the oxygen.
Yes, we control the flame, so there is oxygen left over.
Gotcha.
And then the oxygen will oxidize the metal.
Okay.
And the oxidized metal or metal oxide will evaporate because it's very hot.
Okay.
So the surface will start to evaporate, generate
And so you
vapor.
get now these things in the air.
Yes, but we want to keep them in the vapor phase.
Yes.
And then we put another, we call it substrate, almost like a collecting material.
Yes.
And that is at a cooler temperature.
Right.
And then the vapor will condense.
Okay.
Then we can control this process to control the morphology of.
So as it condenses, based on how quickly you cool it and what the properties of this collecting material are, you can get it to be relatively consistent set of sizes.
Yes.
And so when you do your experiments, you say which size is the best for making hydrogen peroxide in water.
Yes.
Wonderful.
Yes.
So okay. This is the future of everything. I'm Russ Altman, and I'm speaking with Xiaolin Zheng about the uses of combustion, and in this case, for doing chemistry that yields nanoparticles that can be used for many of these catalytic reactions that you're studying. So I wanted to ask, what is the future of this technology in terms of scaling it up and getting it to the outside world? There's always a difference between intriguing initial results in the lab and then a solution that we can deliver to the world. When does your work end, and then who do you pass it off to? Or do you pass it off? Or do you say, I have to now start a company to make sure we can scale this up? How does that translational process work for you?
I'm constantly thinking about this question.
Yes.
I don't have an easy answer. I think I fully agree with you. What we have in the lab is far away from the real application because of their many unexpected challenges. So I feel that the current step we're taking is the one we have was a very beaker type of reactor, very simple. And in real applications, the water will flow because we cannot just treat a small volume of water. The water will
yes, this is a good point.
Yes. So in that case, we want to build a fuel cell-like reactor. The water will flow in, and then we measure the hydrogen peroxide production.
Yes.
And then the next thing is the stability, right? Because as we're purifying the water, we don't want to introduce any impurities, additional contaminants.
Right, because there is all of this tungsten and stuff that you've created.
Yes, so we want to make sure the metal oxide is stable, or how stable it is, right? And the current material we reported is not very environmental friendly.
Right.
And we have identified some better materials. So that's the material stability. I think the third thing is the water, if they're not clean, that means they have many unknown impurities in there.
Yes.
How those things will interfere with the water oxidation reactions is totally unknown. Yeah.
So some of them might not just be bystanders. They might actually mess up the reactions that you want to happen. Like if they consume hydrogen peroxide for some reason.
Yeah, or maybe they're sulfur, they poison the catalyst.
Right.
Yeah, so there are many unknowns. But I think this is very interesting because as we think about practice, it will be departure away from the very idealized system we are studying, and it actually is a richer problem.
So how do you make the decision as a scientist whether you're going to focus on the basic stuff, the basic combustion, get the basic things working, versus all of these engineering challenges to create a device where water flows in, reactions happen, you make sure that water flows out and it's cleaner and it's not filled with impurities. This is what you described.
Yeah.
Do you consider it your job to do that, or are you going to hand it off to a different type of set of engineers to do this work and you just consult with them? How do you think about that?
I always think I'm an engineer because I'm in engineering
You are.
department. Yes. So,
Two of them.
Yeah, so I don't want to say I shouldn't outsource all the engineering problem because
Right.
even this engineering problem, there are a lot of fundamental research involved.
Yes.
So I would like to take on some of those things, like to mention those topics. I would like to start it myself because we still need a well-controlled experiments, and it's not simply just try many things.
So this is exciting because this means you might now start going out into the field and getting samples of real water that needs to be purified and then characterizing that water so you know who are the bad guys in there and what are the challenges that they raise for your technology. Is that the kind of thing you might do?
Yes. Yeah, we will purposely introduce some impurities to the water and to see what happens. Yeah.
This is The Future of Everything. I'm Russ Altman. More with Dr. Xiaolin Zheng about the uses of combustion in engineering next on SiriusXM Insight 121.
From the campus of Stanford University.
People are worried about data. They're worried about their privacy and their security. They should be. We need secure systems.
This is the future of everything.
But we can't have a system that closes that data off. It is too rich of a source of inspiration, innovation, and discovery for new things in medicine.
With your host, Russ Altman.
Welcome back to The Future of Everything. I'm Russ Altman, and I'm speaking with Xiaolin Zheng about water purification, and the challenges of turning dirty water into clean water. And I want to go a little bit thinking globally. If you can help me understand, what is the magnitude of the water problem in Earth? Is this a big problem? I think it is. And what are the big contributors to this problem?
So according to the statistics, about over 2 billion people, maybe close to 3 billion people right now have no access to very clean water. So that's almost 1 out of 3 population, Earth's population doesn't have good quality water.
So this is a huge problem, and in many of those people may be near water sources, but those sources are just not acceptable for human consumption. So this drives a lot of the importance of your work. And I also wanted to ask about green technologies. When we think about water purification, as you mentioned earlier, a lot of people think about, let's add chlorine to the water. And I guess chlorine does some of the things that hydrogen peroxide does, although probably not exactly the same. What are the relative trade-offs between using chlorine and using hydrogen peroxide in terms of sustainability and side effects for the environment?
I see. So chlorine comparing to hydrogen peroxide, they have pros and cons. Chlorine definitely is very effective. It's used everywhere. It can kill the pathogens in water very effectively.
Okay.
The side effect of chlorine is the taste from the swimming pool,
Yes.
right? And it can cause allergy, and they just have that unpleasant odor.
Yeah, I think skin problems and even asthma.
Yes. Like when I go swimming, I always get allergy afterwards because of the chlorine. Hydrogen peroxide, in that sense, is much cleaner. It actually is very green.
Okay.
Because after hydrogen peroxide does its job, it will decompose it to water and oxygen.
Well, that almost seems too good to be true.
Yes, because you only have hydrogen and oxygen.
Right.
You cannot have other compounds there.
So that is about as green as you can get if your compound. Now, if your compound is turning into water and oxygen, which are two obviously pretty friendly molecules on Earth. But let's go back because you said chlorine is good at killing pathogens, and we talked about peroxide, hydrogen peroxide, also doing that. But I remember from our earlier discussion there were two other things that hydrogen peroxide did. One was the heavy metals, and one was the organic compounds. How does chlorine stack up on those two fronts?
Hydrogen peroxide is better for the inorganic and organic compounds, but hydrogen peroxide is less effective in killing the pathogens.
So it's a trade-off there.
Yes, so hydrogen peroxide is not approved to be alone for water treatment, for drinking water. It has to be combined with either UV light or ozone. So in that case, the hydrogen peroxide will be further oxidized to hydroxy radicals, like OH radicals.
Yes.
And OH radical is very effective in killing those pathogens.
I see. So you mentioned ozone and
UV light.
and OH and UV light. So these are so if you do build this box that we were talking about, the box that you're going to ship to the world, that box, in addition to creating those metals that are going to create the hydrogen peroxide, may also need to use UV light.
Yes.
And is that separately the free radicals, or will the UV light create the radicals?
The UV light will create the radical, will turn the hydrogen peroxide to OH radicals.
Very good. And then that will get a killing level for the pathogens that's similar to chlorine, make chlorine relatively unnecessary.
Yes.
And presumably we'll also be able to have our pool guys, for people who have pool guys. The pool guys will be able to use similar technologies.
Yes.
Now, I'm not sure if I'm imagining this, but is bromine also used like chlorine?
Yes.
And I would guess it because they're similar in the periodic table, that they have similar benefits and costs?
Yes. They have similar chemical properties. So I think for the pool guy, it's a little bit better because for normal swimming pool, they have a large surface area and then they have good sunshine for outdoors.
Yes.
And so they naturally get UV. So you may now the additional UV supply for that system.
Gotcha.
Yes.
So then it may be just the hydrogen peroxide that you need.
Yes.
Now, when we think also about the large scale of the water problem, what kind of infrastructure might we need for purification? I'm thinking, okay, let's say you build your technology and we have vast bodies of water. Are we going to have to build entirely new infrastructure for the water system to have large volumes of water going through these processes, or does it already exist? How much infrastructure is going to be required to support your new technologies in the distant future?
Yeah. So I'm thinking more towards to portable version.
Okay.
Because if you want to build infrastructure, that's already the barrier for most people. Yeah. That's why they don't have access to clean water. And we're thinking about for like a personal or a single family use, we have a small portable device. And then they can treat a small amount of water just for their daily
as you need it type of.
Yes.
This is The Future of Everything. I'm Russ Altman. I'm speaking with Xiaolin Zheng about water purity and the global and green opportunities for water purification with hydrogen peroxide and many of its kind of remarkable properties. So just to get a little bit crazy, let's think about the missions to other planets. So one of the issues is I think there's a movement to send astronauts to Mars. That's going to be a multi-year journey. They're going to need clean water. Could you imagine these technologies being part of a system for recycled water, or is that too much of a burden on the technology?
I think it could be part of the system for recycling the water, because if you think about robots on Mars, right, they have solar panels.
Yes.
And for our system, all we need is solar, some electricity, and doesn't need a lot of high voltage. 1.5, like a battery, is sufficient voltage input into the system. And then this can be through with additional filtration system and this hydrogen peroxide, we're using water to clean the water itself.
Yeah.
So I think it's in the wild dream is totally possible in principle.
As long as you don't get too far from the sun, because the solar
Yes.
aspect of it is very important.
Yes.
Now, as we think about these portable units, I mean, I love this idea because it just seems like very attractive, especially for the reasons you mentioned about we don't need to build huge factories that are putting large volumes of water. When can people expect to see these things in their everyday life? So somebody who's getting very excited about these possibilities, and they've heard that you're doing a lot of basic science, that you're trying to think about the way to translate this. What is your timeline for the arrival of these technologies as real marketplace options?
I tend to be more conservative in predicting those
Probably a
things.
good idea.
Yes. I think it's...
Especially since we're taping you.
Yes. I think it still will take 2 to 3 years just fundamental research in my own lab to tackle all those factors we discussed for me to feel comfortable to go for a commercial level of startup.
Okay,
Yes.
so this is good. No, this is a very honest answer. So
Yes.
what I'm hearing, and tell me if I'm getting this wrong, there still is substantial fundamental research, and we know what it is from our previous discussion. You're going to look at other contaminants, make sure that they don't foul up
Yes.
the reactions. You have to have a very realistic understanding of
Yes.
it may be that there are types of polluted water that you just can't do because they mess up your reactions, but
Yes.
other types are well suited.
Yeah.
And there's at least a few years, 2, 3, maybe 5. At that point, is that when we start creating companies that have products in mind and they attract investment, probably from either from people who are in the water industry and they see this as a new technology, or perhaps even from foundations and people who are worried about the developing world and want to get solutions to them. And then you have your normal lifetime of a company, which has to, in about 5-ish years, start to have some products, otherwise they run out of money.
Yes.
So that's pretty exciting because the picture that and again, don't let me put words in your mouth, but I'm hearing that it's possible that in a decade we will have the first incarnations of these machines for focused applications.
Yes, not from my lab,
Right.
because of the need is there.
Yes.
I think many people will try to do that. And because water is such an important ingredient for our daily life, right, for the quality of life. And we have to take a very responsible role. If we say we are going to do water disinfection, we better make sure that water quality is good.
Thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.